Learning journey starts now. Ever wondered why some forces are short range? Gluons, the carriers of the strong force, should be massless like photons, but they're trapped inside protons. Why? That's the heart of the Yang-Mills mass gap problem, one of the Millennium Prize challenges. We need a quantum theory on flat spacetime R4 that behaves like classical gauge fields, but has a minimum energy above the vacuum. So how do we tackle this beast? Forget thinking about individual field values as independent things. That's too messy. The real insight is, the physical state isn't just one potential A, it's its entire equivalence class under gauge transformations, the whole orbit A. Think of it like identifying an object by its shape, not just one specific snapshot. Crucially, open edges in your field description? Just gauge fluff. What matters is the closed loops, the actual curvature, the provenance. This shift means the vacuum omega becomes uniquely defined with zero poles, while any excited state must carry at least one irreducible closed excitation pole. It's about what persists after all the gauge redundancy is stripped away. Okay, so we have the vacuum unique zero energy H omega equals 0. And we have excited states, each carrying at least one of these special poles. Now here's the kicker. Principle Y9 states that these closed excitation poles cannot be erased by refinement or gauge changes. They carry a fundamental minimum positive energy, mu sub g. So if a state isn't a vacuum, it has at least one pole, meaning its energy E of psi is at least mu sub g. Boom. The spectrum of the Hamiltonian H jumps directly from 0 to at least mu sub g. No sneaky excitations hiding in between. The mass delta is simply this mu sub g. It's not an extra term you add, it's the intrinsic energy cost of having a non-trivial, physically distinct excitation. How does this proof actually hang together? It's a beautiful chain reaction. First, we build finite manageable representations of the gauge field in small regions. Second, we use the gauge orbit quotient to surgically remove all the open edge redundancies without touching the crucial closed provenance. Third, refinement compatibility ensures that when we zoom in, we don't accidentally create new independent sources or erase existing ones. Fourth, these compatible pieces assemble into a reflection-positive continuum object. Finally, the unique zero-pole vacuum and the fact that every non-vacuum state must have at least one pole with energy mu sub g gives us the mass gap. Its existence built from finite, verifiable steps, not relying on vague infinite limits. To make this concrete, there's an S3 demonstrator. It crunches through all possibilities for a single plaquette, showing exactly how the orbit quotienting works, how refinement doesn't erase poles, and how the spectrum clearly shows the gap mu sub g. Of course, this is just a toy model. The real challenge is proving this universally for all compact simple Lie groups and formally linking it back to the standard axioms like Osterwalder-Schrader or Whiteman. That's the next frontier. Inside this new framework, the proof feels complete. The external certification, getting the community to agree, is still the final step. Thanks for tuning in.